Okay, so we started with this requirement for phase equilibrium and for coexistence of two phases. The Gibbs free energy in one of the phases has to be equal to the other, and this has to also adhere to the temperature in each one has to be the same, and of course the pressure in each one has to be equal. Otherwise, there's a driving force for molecules to change and to move around until it reaches some sort of equilibrium. Now, we were talking about, just in the previous lecture, the definition of what fugacity is, and also about how to calculate fugacity. It's still, at this point, I'm sure, is a bit esoteric. I mean, we have our Gibbs free energy up here in the equation. So what, and we talked about this being simpler form, it looks more complicated by the minute, but what can we do with this? And so let's just make this quick substitution. If we say that now phi 1 is equal to F fugacity 1 over P, okay, this is equal to EXP. We're going to assume that the temperatures are equal and the pressures are equal, so just T equals T and P equals P. Of the Gibbs free energy of our real material in the phase 1, temperature and pressure, minus the Gibbs free energy of the ideal gas, temperature and pressure all over RT. And then, of course, for phase 2, it's the same equation, just with 2's everywhere, equals fugacity 2 over pressure, equals EXP to the G in phase 2, temperature comma pressure minus G ideal gas at temperature and pressure, all divided by RT. Okay, so what is the first thing you do? Well, the first thing you do is take a natural log of both sides. Ln of F1 over P will simply be equal to G in phase 1, temperature, pressure minus G, IG at temperature and pressure, okay, all divided by RT. Let's just move the RT over to this side. So we have RT log of this process. And you do the same thing for the second material, and you end up with RT ln of F2 over P equals G2, temperature comma pressure, minus GIG, okay, temperature and pressure. If you rearrange these equations, you end up with then for G1 equals G2 gives us G ideal gas at pressure comma temperature plus RT ln F1 over P equals GIG P comma T, or T comma P, I switched the order of those, sorry about that, plus RT ln F2 over P. And so, of course, the ideal gas Gibbs free energies cancel out, the RTs cancel out, take the exponential of both sides, get rid of the pressure, and you have F1 equals F2, or phi1 equals phi2. So even though we transformed the Gibbs free energy by an exponential, the requirement for equilibrium is now that the fugacities are equal, or the fugacity coefficients are equal. And this is the first step in the numerics of making this problem easier.